ArcSan is now digital.ai. Join us at our booth in the virtual expo hall to learn how our app protection, white box cryptography, and threat analytics solutions can help you stay ahead of the evolving threat landscape.
Hi, I'm Steve Springett. I spend a tremendous amount of time researching and working on projects to help improve software supply chains. I'm the creator of Dependency Track, a flagship OWASP project that identifies risks to the use of software bill of materials. I'm also the creator of one such software bill of materials spec called Cyclone DX. I'm the co-author of and project lead for this project, the OWASP Software Component Verification Standard, and I'm also part of the team creating the package URL specification. I was one of the first contributors to OWASP Dependency Check going back to 2012 or 2013, and I participate in a lot of working groups discussing software transparency. Now, all of that is extracurricular. What I actually get paid to do is software security architecture at ServiceNow.
I'm JC Herz, and my main focus is software supply chain assurance for critical infrastructure. So these are systems we rely on for safety, energy, healthcare, telecommunications, and national defense. They're more or less under constant attack by criminal organizations and state actors. So basically, I'm using software supply chain assurance at scale to try to prevent the zombie apocalypse. Also, I co-chair a Department of Commerce working group on software bill of materials, which has contributed to an SBOM requirement for medical devices to have an SBOM as a condition of FDA approval and use in the United States.
Let's start off with a very simple question. How confident are you in knowing the software you think you're building is actually what's being produced? Now, I want you to think about all the things that are involved in making this happen. There's continuous integration servers, source code repositories, SDKs, compilers, package managers, package repositories, distribution networks, and the operating system, network transports, and services that tie everything together. Now, how confident are you in knowing the software you think you're building is actually what's being produced? After all, you have a build script and a repeatable build. What could possibly go wrong?
Even if you do have a handle on the pedigree and provenance of your own software, can you say the same for your suppliers? Most of the software used by organizations isn't produced in-house, and it isn't provided as open source code. It's vendor products, outsourced applications, managed services. We all love DevOps and SecDevOps, but at some point, this preoccupation with first-party pipelines is like looking under the lamppost for your keys, because that's where the light is, not where you lost them.
A long time ago, back in 2013, OWASP added a new entry to the OWASP Top 10, A9, using components with known vulnerabilities. Now, security researchers always knew that using third-party and open source components carried risk. But it wasn't until 2012 when AppSec Security conducted the necessary research that proved that using open source components carried with it inherited risk. The research paved the way for making A9 possible. And this led to the creation of tools. One of the very first tools was OWASP Dependency Check, started by Jeremy Long back in 2012. But many other tools and tool vendors came to be. Existing tools that focused on open source license use cases now had a need to support security use cases. And brand new security first tools were created as well. And this is how the software composition analysis, or SCA, market came to be. Today, SCA focuses primarily on determining if components have known vulnerabilities, if they are out of date or not, or whether the components used meet or violate organizational license policies. When most people think about SCA, these are the three things that are top of mind. Now, has SCA improved software assurance? Yeah, I think so, somewhat. SCA can undoubtedly identify known vulnerabilities in third-party and open source components. So by that measurement alone, yes, SCA has improved software security.
So the next question is, has SCA improved software assurance? Yes and no. It has, to the degree that software scans at points in time have revealed vulnerabilities that first parties have remediated to some extent, either because they're responsible suppliers, anyone who's doing this, good on ya, or because vulnerabilities have been disclosed to them by a third party, by security researchers, by their own customers' assurance teams, or worst of all, by a breach of their capabilities. There are discontinuities in a multi-tier supply chain. The time it takes a supplier to detect a risk when not every piece of software is built every day. The time it takes to remediate vulnerabilities, document a new release, and deliver an update. All of those discontinuities leave end users in the blind, and that's got to stop. There are safety implications, and critical infrastructure needs a way to differentiate responsible suppliers.
A few months ago, the Atlantic Council published a paper called Breaking Trust: Shades of Crisis Across an Insecure Software Supply Chain. There's a link to the paper in the reference slide. The paper provides an in-depth view of many of the things that are inherently broken in a typical software supply chain. This illustration is an example of a multi-tier supplier network. Starting on the left with system design, we see there is the potential to compromise the development process through various certificate, credential, and injection attacks. So even before the code is written or built, we could potentially compromise the systems in which the software will be built. Moving a bit to the right, we see the use of software development kits or SDKs. This could be anything from the .NET framework, the Java development kit, or Node.js. So questions. Does the SDK have a backdoor? Can it embed malware in the software that it builds? Do you know? Are you sure? Because this has happened many, many times before. Moving a bit to the right, we see the use of third-party and open source dependencies being used in our development process. This is where traditional SCA plays a small role. And I say small because SCA will analyze the components themselves, not the repositories in which the components are retrieved from. Has the repo been compromised? Does the build environment have flawed network or package management settings that are redirecting requests to our repo with malicious packages? If the repo is internal, is there an internal threat? Maybe. Moving further to the right, we see that the built artifacts are being deployed. Do we know that the deployment pipeline has inadvertently injected malicious software into our artifacts, or that pre-built artifacts controlled by the attacker aren't being deployed instead? Our deployment may end up being published to a repository such as Maven Central or NPM, or maybe deployed to an internal repo. In either case, others could potentially reuse the malicious component I unknowingly published. And if the artifact was published to an app store, then users within that entire ecosystem could become victims. Maintenance and updates, especially over-the-air updates, carry a tremendous amount of risk. So as you can see, a typical software development process has a lot of unknowns, a lot of potential risk that needs to be mitigated in order to increase the assurance of what you think you're building is actually what's being delivered. So as the OWASP software component verification standard is designed to help organizations measure and improve software supply chain assurance. Now, SCVS is broken down into 6 control families. Each one of these control families could be a talk in and of its own, but let's review them at a high level. The first is inventory. Now, this should be obvious, but knowing what components are in your software is required in order for you to determine if those components carry inherited risk. It turns out that identifying a complete and accurate inventory is kind of hard. Who knew? So SCA tools do this in 2 different ways: binary analysis and manifest analysis. Binary analysis looks at the artifacts and does a sniff test. I think this component is jQuery because it looks like or smells like jQuery. Then there's manifest analysis, which looks at the package manager's manifest file, like your pom.xml or your package-lock.json, and assumes the inventory in those files are accurate. Now, both methods of analysis are educated guesses. Both methods are guaranteed to produce an inaccurate and incomplete inventory. Now, it's possible to come close, but accuracy and completeness will vary widely based on the tool and the method of analysis and the code base being analyzed. But there's actually a third and complementary way of creating such inventory. Turns out that sometimes you get better and more complete results if you simply ask the development teams, hey, what's in your stuff? Software bill of materials, or SBOMs, is a way to do that. SBOMs can be created at build time and can be augmented and corrected by the development team during the build process. For example, if the team made a modification to jQuery and they embedded another library into a custom version of jQuery, the SBOMs, the modifications can be captured in an SBOM so that tools that analyze them don't have to guess. The SBOM should ideally be an accurate and complete inventory of the components. But the beautiful thing about SBOMs is that it puts the power back into the hands of the development teams. They're the ones who know best what's in their software. They're the ones who can augment and correct the inventory and do so through automation. SBOMs are the list of ingredients, the names and versions of components, the license and copyright information, and they'll include provenance information such as where the component was retrieved from and who the supplier was. All of this information can be used to identify various forms of risk. Hardening build environments is also necessary to increase software supply chain assurance. The continuous integration server, the administration of them, the underlying operating system, DNS and network settings, and certificate trust stores are some of the many things that need to be hardened to increase assurance. For example, setting up an SDK on an OS, running a CI server, all with default configurations is essentially flying blind. You'll have no idea, no assurance that the software you think you're producing is actually what's being produced. The use of package managers is the fourth control family. Everyone should use a package manager. Let me repeat, everyone should be using a package manager. The benefits of using them far exceed potential risk. Even for high assurance environments that never trust public repositories and compile all open source software themselves should use a package manager. And C and C+ projects, there's no excuse not to use them. They've been available for the past decade, yet very few C and C+ projects actually use them, which is really a shame. Well, there are many benefits of using package managers. Two of my personal favorites is being, one, able to determine if a component is out of date or not, and two, being able to recall a component. Being able to recall physical items such as automobile parts, pharmaceuticals, or various food items greatly improves public safety. The use of package managers and subsequent package repositories can have a similar effect. Packages that have backdoors or other malicious code can be removed from the repo. This improves security and potentially public safety depending on the use case. The fifth control family is component analysis. This is really about looking at the SBOM and everything inside of it and determining if the components have known vulnerabilities. Are they out of date or not? Are they end of support or not? Do they have license risk? But it also looks at potential architectural risk as well, such as identifying if the component is a library versus a framework and what the purpose of the component is. Is it an XML parser? Because I already have one in my software. I don't need another one. And finally, we look at pedigree and provenance. I always think of provenance as an origin story, where the component was retrieved from, who the supplier is, who's the manufacturer. Whereas pedigree is more about individual DNA. Does the component have modifications? What specific modifications were made? What SDKs and compilers were used to produce the component? So pedigree and provenance round out the sixth and final control family.
SCVS is designed with 3 levels of verification based on the level of assurance required by different kinds of customers. All these controls are geared for automation. This is not a document drill or some carnival of labor-intensive self-attestation. But even with automation, diligence has a cost, and every cost involves trade-offs. The justifiable cost of assurance for a video game is not the same as a payment system or an electrical grid operator. The controls at different levels of SCVS track to the legal and regulatory requirements of software end users, the ones they have to satisfy in order to accept and manage third-party risk and achieve assurance on an ongoing basis. What are the risks in this third-party application in my environment today, and what can I do about it with or without support from the supplier? These verification methods can be implemented over time. This is not an all or nothing sorting hat. There are table stakes, which are level 1 best practices that are achievable and automatable with modern engineering workflows and open source tools. Beyond that, verification methods can be adopted one by one, as desired or as required by end users as an acceptance condition.
Are SCVS control requirements measurable? Absolutely. The overwhelming majority of controls can be verified through automation. We discussed network settings and package management settings and the use of SBOMs. All of these things and more can be verified through automation. In addition, SCVS measurements can be observed by the organizations implementing them or by a consultancy in the event that attestation needs to be provided.
More security-conscious customers will be quicker to adopt these verification requirements. Adoption by less security-conscious customers will be slower. Adoption by recreational coders will be never. But the thing to remember for end users and suppliers is that adoption goes beyond IT. These requirements are measurable and verifiable, so they're auditable. Security and compliance people are going to set these criteria based on what their lawyers tell them. Procurement has a role to play. There are already financial institutions that firewall procurement based on software bills and materials. You're going to see security SLAs for dependency updates. I thought about saying winter is coming, but maybe it's spring. Depends on your perspective, I guess. In any case, this and other software transparencies initiative in flight has implications for commercial software vendors, contract application developers, and ultimately for the open source ecosystem itself.
So where can you find more information? I'm glad you asked. OWASP.org/SCVS is your starting point. There you'll have access to project information, links to the GitHub repo, as well as the ability to download or read the standard online. Here are a few links to get you started. The SCVS project page has download links in various formats, including Microsoft Word, PDF, JSON, and XML. Or use the Gitbook URL to read the standard online. No download required. The third link is the Atlantic Council paper I mentioned earlier. I highly suggest everyone read through it. It's a fascinating and in-depth analysis of many of the things that could potentially go wrong in a typical software supply chain. The paper also has references to much of the raw data that was used as well. Thank you for watching, for listening. It's going to take a collective effort, but together we can improve the assurance of our respective software supply chains.